Welcome back. So we were formalizing our setup to study performance of training algorithms for decentralized deep learning. And we talked about basically our communication graph, the weight matrix. We talked about basically the assumption that it is undirected and it's also doubly stochastic, meaning that all the weights are non-negative. If there is no connection between the agents, we set the weight to be 0. The diagonal entries are strictly positive because each agent can communicate with itself. And we also said that there is some normalization happening, which meant that rows sum to 1. And so therefore our weight matrix is a row stochastic matrix. And also the columns sum to 1 because it's a symmetric matrix. So therefore our graph or our weight matrix is a doubly stochastic matrix. All right. So now we want to talk about basically again the implication for training and optimization. So what's our goal? So recall our goal was to basically find this common solution W star, which minimizes the average loss. So such that after the training, everyone has access to this W star. Okay. So we are minimizing the average loss. Each local loss is basically some stochastic function, which again we think of it as the average loss over the local training data, okay, for agent J. All right, and again we want the solution to be W star, so they should reach a consensus. All right, so to gain some intuition, let's first start with a much simpler problem. So let's say, for instance, that our loss function is basically given by something like this. So the local loss is essentially a convex quadratic function. Okay. So FJs, the local loss functions, are strongly convex. They are smooth, very nice convex quadratic functions. And we know that some of the convex function is also convex. So the global loss, the average loss, is also strongly convex. So what does that mean? It means that if a genie, let's say, had access to all of these local loss functions, it could very easily find the optimal solution to the average loss. All that it takes is to take the gradient, set it equal to 0. Okay? So first order optimality implies global optimality for convex functions. So if you do this calculation, which is again very easy, you're going to see that the optimal solution will be the average of these xj's. So what are xj's? Xj's are basically some local information that agent J holds. Okay. So in this case, W star will be basically the average of these local informations. Okay. So it's like I'm holding a number, you're holding a number, our friend is holding a number, and in this case, the solution we are looking for is the average of the numbers we are holding. Okay. So therefore, in this case, what we are doing, we are hoping to find the average. Okay? And if the graph is basically not a fully connected graph, we are hoping to find the average by communicating with each other. Okay? So this problem is actually called average consensus. So when F is as simple as this, what we want to do, we want to basically reach consensus over a decentralized communication graph. Okay. Now, if our graph was fully connected, this was very easy, right? Because by just one exchange of information, I would have access to everyone's number, and other agents will also have access to everyone's number. So they could basically just very easily find the average, and will be done in exactly one shot, in exactly one round of communication. However, when the graph is not fully connected, that means that I may not be connected to, let's say, agent 10. So the agent 10 is not going to be is not going to have access to my local information immediately. But because we are assuming that the graph is connected, as we keep communicating, my information eventually, with some delay, is going to find its way to agent 10. So eventually, after certain rounds of communication, we should be able to actually find the average. Okay. So we basically want to talk about this iterative algorithm that I talked about, okay? Such that we can solve this average consensus over general graphs that are not necessarily fully connected. All right. So let's see how one could approach this. Okay. So let's first of all define the matrix, because I think the easiest way to talk about this is actually in the matrix notation. So let's define a matrix. Oh, by the way, so I'm going to use this notation that instead of W star, I'm going to use X bar. Okay, because again, this is a somewhat the universal symbol for finding an average quantity. Okay, so in this simple problem, we are interested in the average. So I'm just going to call this X bar. Okay. All right. So let's define this matrix then. So matrix X bar is basically a matrix that holds that has identical columns. Each column is exactly equal to this average number. Okay. So column 1 is X bar, column 2 is also X bar, column 3 is X bar, etc. So it turns out this is basically just a product of the outer product of X bar and the vector of all ones. Okay. Now let's do a quick check. So I want to basically see what will happen if I multiply this matrix that I just defined with this other matrix, 1 over k, 1, 1 transpose. What is this matrix? So it should be relatively clear that this is a matrix that every entry is equal to 1. Okay, something like this. So all entries are exactly the same. Every entry is equal to 1. Okay. So therefore, in terms of our weighted graph and communication graph, this is like a basically like a fully connected graph. So this could be thought of as the weight matrix associated with a fully connected graph. Okay. All right. So I multiply X bar with this 1 over k 1 1 transpose. So we just mentioned that X bar is exactly the octator product of X bar and 1. Okay. So it should be relatively easy to see that this will be, after some simplification, exactly equal to X bar. Okay. So if I multiply X bar with this matrix, I get back X bar. It is a fixed point. Okay. So it's not changing. And as I just mentioned, this if I call this matrix W, this can be thought of as being the weight matrix of a fully connected graph. So basically, therefore, what we are saying is that we have this equation, at least for a fully connected graph, that X bar, a matrix that holds this average value as its columns, is equal to X bar times W. Okay. So therefore, if I think of this, let's say, as some function h of X bar, I have what this condition is saying is that is saying that h X bar is equal to X bar. So therefore, X bar is a fixed point of this function h. Okay. Now it turns out that again, so what we are stating here again is, and we just showed, is true for fully connected graphs with this specific weight matrix. But it turns out that this is actually true for all connected graphs with any doubly stochastic matrix W. Okay. So what does that mean then? So X bar is basically the average quantity I'm looking for. So again, remember our goal is to solve the average consensus problem. So I want to find X bar. X bar is the fixed point of this function. Okay. So how can we find the fixed points? Well, there is a simple algorithm, fixed point iteration. Okay. So which basically says that X bar, your estimate at X bar at time, let's say t plus 1, is just h of X bar t. Okay. This is called fixed point iteration. Very simple algorithm. And in fact, if you recall, we talked about this algorithm earlier in the class as when we introduced gradient descent. Okay, so there is actually a connection between gradient descent and fixed point iteration, such that again, if we want to find a stationary point of a function such that the gradient is 0, we can think of it as a fixed point problem. And fixed point iteration with some modification becomes exactly like gradient descent. So therefore, in this case, for any connected graph with a given weight matrix W, as long as the weight matrix is doubly stochastic, we are dealing with a fixed point problem. So we can apply fixed point iteration and calculate the average quantity. It's an iterative algorithm, which means that it's going to take some certain number of iterations such that we can find a very good, highly accurate estimation of the average number. Okay. So this is our method then. So we localize the initial solutions. Okay. So these are basically the local vectors, the local numbers that we are all holding as agents participating in this training problem. And we're going to run the following local steps for t number of iterations. Again, this is very easy to see. It's just a fixed point iteration for the problem we just talked about. But what's the sort of the implication, right? So what are we doing? So what's the interpretation of this? So it's best to see it out of the matrix form. So from the perspective of each agent. So it turns out that this is going to be equivalent to this equation I'm writing on the left-hand side. So what we are doing, we are aggregating the messages we are receiving from our neighbors, okay? So we are doing a weighted aggregation, a local weighted aggregation. I receive one message from agent 1, another message from agent 2. I also receive a message from myself. So what I do, I multiply the first message with its weight, the second message with its weight, and my own message with my own weight, and then sum it up. Okay? So therefore, we are doing local aggregation. And this is indeed a weighted averaging, right? So because remember, we assume that the W's, the rows and the columns sum to 1. So we are doing a weighted average over the messages we are receiving from our immediate neighbors. Okay. So what is this matrix X that I'm talking about? Again, this is a matrix that holds the local estimates of the average at time t. Okay. So at any given time, given that the graph is not fully connected, we are not at consensus. So this matrix xt, which is the estimate of the average at time t, does not necessarily have identical columns. But the hope is that as we keep running this algorithm, all the columns become identical, and they're going to become exactly the average number we are looking for. All right, so this is the average consensus method. So it's an iterative algorithm. It's natural to talk about this convergence then. And it turns out that, again, we can have this extremely simple theorem. The proof is simple thanks to this connection to fixed point iteration I just talked about. So if the graph is connected and the weight matrix is W stochastic, let us define the consensus error. So that means that at time t, how far I am from, or how far all agents collectively are from the average number. Okay. And again, we can write it equivalently in two terms in the matrix form. So that's just the norm difference of the current estimate xt and x bar, what we are looking for. So here we are using the Frobenius norm. Or in terms of the local estimates that agent is holding, what we are doing, we are basically taking an average over the local errors of agents. Okay. All right. So then, thanks to this connection to fixed point I talked about, by using the famous Banach fixed point theorem, we can show that the error, the consensus error, reduces at a linear rate, exponential rate. So the error at next iteration is the current error times some factor, which is going to be between 0 and 1, as I'm going to mention. So what is this factor? This lambda 2 square. So absolute value of lambda 2 square is basically the second largest eigenvalue of W. So W is a symmetric matrix, but it's not necessarily positive semi-definite. That means that the eigenvalues are real, but they could be negative. Okay. So what we have here is the second largest magnitude. Okay. So for instance, if the eigenvalues are, let's say, 1, minus 0.9, and 0.8, this is what I'm talking about. So the absolute value of lambda 2 in this case would be 0.9. So this will determine the rate of convergence. All right. So so let's talk about this result. So we are assuming that W is doubly stochastic, and basically that means that the rows sum to 1. So this basically means that the vector of all 1 is an eigenvector of matrix W with eigenvalue 1. So one of the eigenvalues we know it is. The others we may not be able to see immediately, but at least we know one of them. And it turns out that this is the maximum eigenvalue. So all the other eigenvalues have a magnitude which is less than 1, okay? Less than or equal to 1. Okay, so so therefore, what we can define is this quantity, the difference between the largest eigenvalue, which is 1, and the second largest eigenvalue. So let's call it rho. So this will be something that is between 0 and 1, because again, all the eigenvalues have a magnitude which is between 0 and 1. Okay, and this is a very important quantity. It is called the spectral gap of W. Okay, this in some sense is a mathematical measure of connectivity of a graph. So if rho is large, that means that we have better connectivity. Okay, so and therefore it means we have faster convergence. On the other hand, when rho is small, we have worse connectivity, and therefore the convergence is slower. And at the extreme case, rho will be equal to 1 when our graph is fully connected, but rho will be equal to 0 when we have a disconnected graph. So this matches our intuition that for fully connected graph, we should immediately converge, because again, everyone is connected to everyone, so we should be able to see their messages quickly, and we should be able to converge in one iteration. So in that case, rho will be equal to 1, which means that the absolute value of lambda 2 will be equal to 0. So in exactly one iteration, the error becomes 0, and we reach consensus. For disconnected graph, it's hopeless, right? So there is no way I can actually see, let's say, the message of an agent that I'm not connected to. So I'm not going to be able to calculate or approximate the average to arbitrary accuracy, arbitrarily high accuracy. So this is the sort of the method we're going to build upon to generalize this idea to general training problems. Remember, here we just worked with a very simple case where our loss functions were a quadratic function, and that corresponded to this average consensus problem. Now we want to see how we can use this idea as well as the what we've talked about before, for instance, in terms of training algorithms such as SGD, to tackle general decentralized deep learning training problems. And we're going to talk about that in the next video. I'll see you there.